Hi, I'm Jessie Freeman, and welcome to Unity 5 2D Introduction to Pathfinding. In this course, we'll look at how pathfinding works. I'll start by explaining each of the different data structures needed to do pathfinding. Then, I'll cover how to connect them up so you can search for a path between two different points on a 2D map. And finally, I'll cover how to visualize your path. We'll be covering all these features in order to better understand the basic foundation of building pathfinding algorithms. Now let's get started with Unity 5 2D Introduction to Pathfinding. This course includes exercise files. Inside of the exercise files folder, you'll find each chapter as well as a final project folder. Inside of a chapter folder are subfolders broken up for each video. Here, you'll find the state of the Unity project for that particular video. This course was originally built with an older version of Unity 5. From time to time, new releases of Unity require you to upgrade the project. This course has been updated to the latest public version of Unity, which is 5.3.4 F1 as of this recording. You'll need the latest version of Unity or above to run this project. If you run into any problems, you can always download older versions of Unity from the website archive. Now let's get started. One of the most common pathfinding algorithms used in many games is A*. In plain English, A* is a way to plot the path from one cell of a grid to another. This is most commonly associated with a tile map or 2D terrain, but can also be applied to 3D games as well. The algorithm simply works its way through each cell until it reaches a destination, or stops when no solution can be achieved. At its core, A* pathfinding relies on a data structure called a graph. A graph is like a table, except each cell has a direct reference to its surrounding neighbors. This last part is key because we use the relationship between these connected cells, which are often referred to as nodes, to help us traverse the area while avoiding obstacles and generate out a path from one node, which is our start position, to another, which is our goal. Using a graph and node is common in a lot of pathfinding algorithms, not just A*. So that's why we're going to focus on that part of the problem here. To get started, let's create a new project in Unity. We're going to call this project Intro to Pathfinding. We're also going to set it to 2D and create the project. Once it's created, let's make a few folders. We'll need a new folder to hold our scenes and another to hold our scripts. Finally, let's save our current scene into our scenes folder, and we'll call it Pathfinding Staging. In the next set of videos, we'll look at the node class and start building out the foundation for our pathfinding logic. A node is the basic building block of our pathfinding algorithm. We use the node to represent each space in the map and its relationship to its neighbors. The node is a critical part of the entire algorithm. So let's look at how to build out our first node class. Inside of our scripts folder, let's create a new C# script, and we're going to call this node. Then let's open this up in MonoDevelop. As we build out the node, we're going to need to keep a list of all of the neighbors that the node is surrounded by. In order to do that, let's change our system collections at the top of our class to systems collection generic so we can have access to the list later on. Next, since our node isn't going to be represented by a game object itself, there's no reason for us to extend monoBehavior. So let's delete that. And also, we can delete the start and update methods. Let's save our script. At this point, we now have the basic shell for our node, and in the next video, we'll talk about the properties that make the node work. Now let's look at the properties that'll make up our node class. The other thing we're going to need to do is keep track of other nodes adjacent to the node we're in. In order to do that, we're going to create a public list and type it to node. Let's call this adjacent, and we'll create a new list to contain these nodes in. Next, we're going to need to make a public field called previous that's typed to node. And let's set this to null. Later on, as we start searching through the nodes, we're going to use this field to keep track of the previous node we looked at as we try to figure out which is the best path for us to go. Finally, let's give our node a label field, and we'll type it to string. We'll use this to give each node a unique name so it's easier for us to look it up later on. The final thing we need to do is add a way to clear our node so that we can reset the previous field. Let's create a public property called clear. And inside of it, we'll set previous to equal null. At this point, we've completed the basic structure of our node. In the next set of videos, we'll look how to link nodes together by using a graph. And now we're ready to build our graph class, which will help us link the nodes together. Let's switch over to Unity and create a new C# script called graph. Then open this up in MonoDevelop. Just like the node class, our graph doesn't need to extend mono behavior, so we can delete that, and we can also remove the start and update methods. Now we'll need some fields to help keep track of the rows and columns of our graph as well as the nodes. Let's start by making a public int field called rows and setting its value to 0. We'll need to do the same thing for columns. And finally, we'll need to make a public array of the nodes we want to keep track of. Let's call this nodes. In the next video, we'll look at how to store the nodes inside of our graph. Now we need to create our graph class's constructor. We'll do this by making a public method called graph with no return. And our constructor will accept a 2D array typed to int, and we'll call it grid. A 2D array is a type of array that has nested arrays inside of it. In this case, it's going to represent the rows and columns of our grid. In our constructor, let's set the value for those two fields of our class. We'll start by setting the rows to the grid length of item 0. And for columns, we'll get the index of 1. Now we're going to need to set up our nodes array. Since each node is going to store a reference to its own neighbors, we can actually keep all of the node data as a flat array inside of our graph. In order to do this though, we're going to need to create enough spaces in the array to match the length of the grid. We can do this by setting the nodes field to a new node array, and inside of it, we'll use the grid's length. Next, we're going to loop through all the spaces in the array and create an empty node. We'll do this with a for loop. Here we'll use the node's length. Here we'll use a for loop. We'll set I to equal 0. We'll make sure that I is less than the node's length, and we'll increase I on each loop. Next, we're going to need to create a node that'll go inside of the array. After we created our node, let's give it a label, and we'll convert the I value from our loop into a string. We'll relate to its position inside of our array. Finally, we'll need to set this new node to a space inside of the array. We'll use the current loop's I position to do that. And now we have a graph that can accept a 2D array representing a tile map and convert this into an array of nodes. In the next video, we'll look at how to index each of the nodes and build the node relationship inside of our grid. Now that we've created our array of nodes, it's time for us to index the grid and build out the nodes association. In order to do this, we're going to need to loop through the grid's rows and columns and pull out the associated node from our nodes array. Let's create a new for loop where we can iterate through each of the rows in the grid. Here we'll create a variable called r to represent each row. We'll make sure that r is less than the total number of rows, and then we'll increment r by 1 over each loop. Inside of this loop, we're going to need to go through each of the columns. So let's create another for loop using the variable c to represent column. Here, we're going to want to make sure that c is less than the total number of columns. And then we'll increment c by 1 over each loop. Next, we'll need to get a reference to the node inside of our nodes array. Let's create a variable for the node, and in the nodes array, we're going to use a little formula in order to figure out how to convert the rows and columns into the correct space in our flat array. We'll start by taking the columns and multiplying them by the row, and then adding the current column back. Next, we're going to want to test if the value of the grid item is a solid wall. Here we'll create a condition and we'll test out the position in the grid based on its row and column in the loop to see if it's equal to 1. If it is, we'll call continue. When we go to build out the grid and our test map, we'll use the value 0 for an open tile and we'll use 1 for a solid tile. In the next video, we're going to go through and test out and if neighbors exist, we'll add them to that node's adjacent list. So now that we have an actual node from our array, let's take a look at its neighbors. After the condition where we test to see if the grid cell is solid, let's create a comment for up so we know which direction we're looking at. In order to do this, we're going to do a condition that takes a look at the current row and make sure that it's greater than 0. Inside of this condition, we're going to add any node above the current node. We'll do this by taking our existing node and then adding the node to its adjacent list. In order to find this, we'll have to look at the nodes array and find the position above the current row and column we're in. We can do this by multiplying the columns by the current row minus 1 and adding the column back to it. Next, we'll look at right. Here, we're going to test if the column is less than the total number of columns minus 1. And inside of this condition, we'll look for the node to the right. In order to do that, we're going to take the columns and multiply it by the row plus the column plus 1. And now let's see if there's a neighbor below our current node. Here, we're going to test if the current row is greater than the rows minus 1. And inside of it, we'll add the neighbor below. In order to do that, we're going to multiply the columns by the current row plus 1 plus the current column. And finally, we'll look to the left. Here, we'll test if the current column is greater than 0. Now we can add the node to the left. In order to do this, we're going to multiply the columns by the current row plus the current column minus 1. And now that we are able to connect a single node to all of its neighbors, we now have a fully functional graph which can accept a 2D array and build out the relationships between each of the nodes for us. In the next set of videos, we'll build out the search class, which will allow us to traverse the graph from one point to another. Now that we have our node and graph class, it's time for us to create a class to search the graph. Inside of Unity, let's create a new C# script called search, and then we'll open this up in MonoDevelop. Let's bring in the generic collections namespace. Also, we're going to delete the mono behavior and the start and update methods. And now we'll need to add some fields to our search class. The first is going to be a reference to the graph we're actually going to search. Let's create a public field. Its type will be graph, and we'll call it graph as well. Next, we'll need to create 3 lists that are typed to node. We'll need one for the reachable nodes, another for explored nodes, and the last for the path through the nodes we've gone through. Now we'll need to keep track of the goal node so we know when to end our search. We'll also want to keep track of the number of iterations our search performs. And finally, we'll need a Boolean to keep track of whether our search has completed. Now let's create our search class's constructor. Here, we're going to pass in a reference to a graph for our search to look through. And we'll set this reference to the graph to our search's own graph field. Now that we've set up the basis of our search class, in the next video, we'll look at how to actually start a search. Now that we have the foundation for our search class, it's time for us to create a way to start the search. In order to do this, we're going to create a new start method outside of our search constructor. This way, we can call start at any time and change the beginning node and the end node. We'll create a public method called start, and inside of it, we'll pass in a node called start and a node called goal. Next, we're going to need to create a new list to keep track of the reachable nodes. We'll also want to add the start node to our reachable list, since we know that the starting place is always reachable. Now let's get a reference to the goal node. Here, we'll set the goal node to equal the goal. Now we'll need to keep track of all the nodes that we've explored during the search. So let's create a new list. And let's also make a new list that'll represent the path through our graph. And finally, we'll want to reset the number of iterations our search has taken. Now before we search, we're going to go through all the nodes in our graph and clear them out in case we've run the search previously. Here we'll create a for loop, setting I to 0 and making sure that I is less than the graph node's total length. Inside of this loop, we'll select the node based on the I value and call clear. And now we've reset all the values of our search so that we can begin going through the graph and trying to find our way from the start to the end goal. Now, in order for us to perform the search, we're going to need to create a method that will allow us to step through one solution at a time. In this case, a solution is going to be testing out a particular node and its neighbors for the next possible move to make. To do this, let's create a new public method called step. Now, inside of this method, we're going to need to create a guard clause. First, we want to make sure that we no longer call step if we've already reached a path to our destination. Let's check that the path list's count value is greater than 0. If it is, we're going to return out of the method so that we don't execute any of the following code we're about to add in. Next, let's make a condition the count of the reachable list. If it equals 0, that means we've run out of options to move and we haven't found a solution, so the search is done. When this happens, we'll set finish to equal true and we'll exit out of the method with a return. Finally, we want to increment the iterations. If we've made it this far in our step, that means we've gone through one single iteration. Another thing to note of why we pulled the step out as its own method is because when we run the search, we're going to continue to keep calling step until finished is triggered as true. This will allow you to run this in the update method of a game object, or you can run this at a certain interval during a frame in order to not lock up the system. If you had lots of AIs trying to find solutions to paths, and you were running this loop over and over again without a break or some sort of pause between a frame, you'd end up overloading the frame. And we also want to keep track of how many times we iterate through our solution in case we want to exit out early. Sometimes if we iterate for too long, we can detect that there is no solution early and exit the loop, so we also don't bog down the system. Now, in order for our step method to work, we're going to need a way to pick a node to start searching with. Let's create a public method with a return type of node, and we'll call it chooseNode. In this method, we're going to return a random node from the reachable list. We'll do this by getting a random range from 0 to the reachable count. Now, normally when you do pathfinding algorithms like A*, you would apply a value to each node to help you to find the next most logical move to make. Since this is just a basic platforming example, we're just going to randomly choose one from the list of reachable nodes. Now let's go back into the step method and get a node by using chooseNode. We'll put this under the number of iterations. Here we'll create a variable called node, and we'll call chooseNode. Now that we have a node, the first thing we want to do is check to see if the node actually equals our goal. If we're at the goal, we need to fill the path into how we got here. We're going to use a while loop to go back over the nodes one by one, saving out the reference to the previously visited node until we get back to the beginning, which should be a null reference in its previous value. Let's create a while loop. Inside of the while loop, we're going to test that node does not equal null. From here, we're going to take the path and insert a new value, which is the node that we're currently looping through. Next, we're going to set node equal to the node's previous value. As we continue to connect up our search logic, we'll be keeping track of the previous node that we visited, so this code will execute correctly. At this point, since we're testing that our node equals the goal node, we're going to want to exit out of this. At the end of this condition now, since we're testing to see if the node equals the goal node, we're going to want to set the finish field to true and exit out of our step method. Here we can do this by creating a return statement. And now we've created a condition that will allow us to test for whether the current node we're looking at is actually the goal. And if it is, we can rebuild the path to this goal by using the node's previous field. So now that we've searched for whether the current node we're looking at equals our goal node, if we haven't reached the end of our search, we're going to want to take the current node that we're looking at and remove it from the reachable list. We also want to add it to the explored list because we're just about to look at it. Below the condition where we test for the node equaling the goal node, let's remove the current node from the reachable list. Next, we're going to add the same node to the explored list. Now before we're able to continue our search, we're going to need to create a method that will allow us to populate the next possible solutions. Let's create a public method called addAdjacent. And we're going to pass in a node as well as the adjacent node. We'll fill this in a little bit later. Let's go back into the bottom of our step method. Now we need to iterate through all of the adjacent nodes attached to the current node that we're searching on. So let's create a for loop to iterate through those. Here we'll set I to 0, and we'll make sure that I is less than the current node's adjacent count. Then we'll increase I by 1. Now, inside of this loop, we're going to call the addAdjacent and pass it in the current node that we're searching at, plus its own adjacent nodes. At this point, our step method is done. We finally added in the ability to remove the nodes that we've already reached, as well as add the nodes that we've already explored. And since we've set up the foundation for adding the adjacent nodes, we'll know where to search next when we call step again. Now, before we can finish out the addAdjacent method, we're going to need to add a stub method for finding the next node. Now, in order for us to complete the addAdjacent method, we're going to need to create a helper method called findNode. Let's make this a public method, and it's going to return a Boolean, and we'll call it findNode. And we'll need to pass in two things, a node and a list of nodes. Now, we're not ready to actually add in the logic for this method. So for right now, we're just going to have it return false. We'll come back to this later. So in order to complete our addAdjacent method, we're going to need to create a condition. Let's start our if statement off by calling findNode and passing in the adjacent node as well as our explored list. We'll also want an OR statement in order for us to test the findNode against the adjacent node and the reachable list. If either of these return true, we're going to exit out of our method. If this doesn't return true, we're going to add the current node to the adjacent node's previous field. This means that we found a new path, and now we're going to add the adjacent node to our reachable list. Now that we have this method complete, our step logic is going to loop through all the adjacent nodes and continue to try to find the next available option. And once it finds that, it'll push that node into the adjacent previous, as well as add it to our reachable list. Now it's time for us to complete our findNode method. We're going to need to create a simple helper method that will allow us to get a node from an index. Let's create a public method. It'll return a type of int, and we'll call it getNodeIndex. Inside of this method, we're going to pass in a node as well as a list of nodes. From here, we're going to iterate through the list and compare to see if the node exists inside of the list. Let's create a for loop. We'll set I to 0, and we'll make sure that I is less than the list count. Next, we'll test if the node is equal to the node in the list at the I index. If it is, we'll return I. At the bottom, outside of our for loop, if we've not found the node in the list, we're going to return the value -1. Now, inside of our findNode method, we can call the getNodeIndex. From here, we'll pass in the node we're searching, as well as the list that gets passed into the findNode method. Then, we'll do a compare to see if it's greater than or equal to 0. This way, if we do find the node, it'll return true. If the getNodeIndex returns -1, we'll return false. At this point, our search class is now complete. So now that we've built our node, our graph, and our search logic, it's time for us to test it all out. Let's go back into Unity. Now, inside of Unity, let's create a new C# script, and we're going to call this pathfinding test. Next, we're going to want to attach the pathfinding test to our main camera. We'll just attach it here so we're able to run it. Now, let's open this up inside of MonoDevelop. In order for us to do a search, we're going to need to create some new map data. Let's create a 2D array typed to int, and we'll call it map. In the constructor, we're going to set up our 2D array to be a 5x5 grid. And then we're going to pre-populate it with our map data. For our first row, we're going to set the values to be 0, 1, 0, 0, and 0. Let's copy this line and paste it 4 more times. On the last line, let's change the 1 to a 0. As you can see, we'll have a pretty open room with a wall along the left middle side. This will give us a good test to see if our pathfinding logic works. Let's save our script. As you can see, we now have a pretty open room with a solid wall along the middle left-hand side. This will be a good test to see if our search algorithm works. Now that we've created our map data, let's create a new graph for us to search with. Here, we'll create a variable called graph and pass in the map data. Next, we'll create a new search. And inside of the search, we'll pass in the graph. Now we're ready to call the start method on the search class. We're going to need 2 nodes. So let's select the first node and the third node from our map data. Now, in order for us to run our search, we're going to need to step through each solution. For this kind of test, we're simply going to use a while search, and we'll check to see if the search is finished. As we continue to loop through during the while, we're going to call the search's step method. Remember, when our step logic is finished and we found a solution or we've run out of options, it'll automatically set the search's finished field to true. Let's add one more line of code. We're going to output the search path count as well as the search iterations. Now, when we run the game, we'll see that our search is completed, and the path from the beginning node to the end node took 11 steps, and it also iterated 19 times in order to find that solution. Now that we know that the search is done, let's stop the game and save our scene. So now that we know that the search is actually working, let's create a way to visualize what the map and our search actually looks like. From the Game Object menu, go to the UI and create a new image. Once we have a new canvas, let's create an empty game object as well. We're going to call the empty game object map group. And let's add a grid layout group component to it. Here, we're going to change the cell size to 16 by 16. We'll give it a spacing of 2 by 2 so we can see each of the tiles inside of our grid. Let's change the child alignment to middle center, and we'll change the constraint to fixed column count, and we'll set this to 5 since our grid is 5 by 5. Now let's drag our image into the map group and double-click on the map group so we can see it in our scene. Let's copy the image and paste it 24 more times so we have our 5 by 5 grid. Let's save our scene and go back into the pathfinding test script. In order for us to work with Unity's new UI, we're going to need to import its namespace. Next, let's create a new public field typed to GameObject, and we'll call it MapGroup. Let's save our script and go back over to Unity. From here, we're going to want to select the main camera, and we'll drag our map group over to the pathfinding test map group field attached to our camera. Now, we have a grid, and we're able to access the grid from within our pathfinding test. Now we're going to need a way to change the color of the images inside of our grid UI object. Let's switch back over to our pathfinding test. After start, now let's create a private method that'll return an image, and we'll call it getImage. We're going to pass it in a string called label. Here we're going to use the label from a node to find the actual image inside of the grid. In order to do that, we're going to have to convert the label to a number. Now, before we can convert this label into a number, we're going to have to import the system namespace. So at the top of our class, let's add that. Now, inside of our getImage method, let's create a new variable called ID, and we'll use int32 to parse the label. Next, we're going to need to get a reference of the game object itself. Now, let's create a variable for the game object we'll need to get. We'll call it Go, and we'll use the map group's transform child. We'll supply in the ID that we just created, and then from that transform, we'll get a reference to its game object. And now, we can return the game object's image component. Next, we're going to need a way to reset all the colors of the map. Let's create a new method called resetMapGroup. Here, we're going to pass in a graph. Inside of this method, we're going to do a for each loop through each of the nodes of the graph, and based on their value, whether they're open or solid, we're going to change their color. Let's start with our for each loop, and we'll create a variable called node, and we'll get it from within our graph nodes array. Next, we're going to call getImage on that node's label and set its color. Now, in order for us to figure out whether the tile is solid or not, we're going to look for the adjacent count. So here we're going to test if the node's adjacent count is equal to 0. If it is, we'll set the color to white. If not, we'll set the color to gray. And now, below where we print out our search results, let's call reset map group, and we'll pass it in the graph. Let's save this and go back into Unity. Now, when we run the game, we'll see that all the tiles change their color. The open tiles will be gray, and the solid tiles will be white. Now that we know this works, we can stop the game. At this point, we're now able to visualize what our map looks like. Let's go back into our code and iterate through our search's path, and we'll change all the nodes in our path list to the color red. After we reset the map group, let's create our for each loop. We'll create a variable called node, and we'll look inside of the search path. From here, we'll call getImage and pass in the node's label. We'll then set the color property to red, and let's save. Now back in Unity, if we run the project, we should see our path. Stop it and run it a few more times. One thing you'll notice is that the path is slightly different each time. One of the reasons behind this is that we aren't using full A-star logic, because we're not weighting each of the nodes, and we're only selecting them randomly. There are chances that the path will deviate off of the best solution. The good news, though, is that you now have a basic foundation and understanding of how pathfinding works. One of the other interesting things about this is that you can actually use the search without having a graph. Let's say you were using a map that wasn't a grid, and you had a node structure, or you wanted to test for multiple sides. You could simply come up with another construct that would expose all the nodes to the search, and this algorithm will search through them as well. Thanks for watching the course. Hopefully you enjoyed it as much as I did making it. If you're looking to learn more about building 2D games in Unity, please check out my Unity 5 2D Essential training. In this video, I teach you how to build a side-scrolling endless runner. If you're looking to learn more about building platformers, also check out my Advanced Unity 2D Platformer Player Movement. And finally, if you're looking to learn how to debug scripts in Unity, also check out Chris Byers' Debugging Scripts in Unity. Thanks again for watching, and see you next time.